Umut Varolgunes, who's going to give his second talk on homological symmetry via Floer theory.
Okay, thank you. Yeah, so in the previous talk, I avoided talking about Floer theory with support, and I kind of tried to give a sketch of the strategy for how my kind of the local to global strategy that I want to use for homological mirror symmetry looks like, kind of in a case where you can use pre-existing invariants. So today, I have to introduce to you this Floer theory. I have to do Floer theory with support, explain that to you. And it's fairly technical, I don't know. So there's also a lot of things in these slides. So the plan is I want to first, okay, now use the strategies. I want to first start with Morse theory with support. Kind of go over that. And kind of this also includes explaining some framework for equipping like symplectic homology type invariants with operatic structures. And then I want to talk a little bit about Floer theory with support on Liouville manifolds. Then a little bit about just closed symplectic manifolds. And then I want to end with our strategy for homological mirror symmetry with Mohammed and Groman. And I think Mohammed is going to give something related after. So hopefully it connects. We didn't discuss before, so I don't know if it will connect.
I haven't prepared yet.
Well, at least I have prepared.
Your next.
Okay. Okay, so let's start with this simple case. So let's say X is a closed manifold, K is a compact subset. And my goal here is to define Morse theory, this kind of Morse-Witten complex of a function that's 0 inside the compact subset and infinity outside. So it's this semi-continuous function, upper semi-continuous function. So, I mean, I do the thing that you imagine we should do is we take a sequence of Morse functions, F1, F2, which are kind of increasing pointwise, and they converge to 0 on K and infinity outside of K. So each of these guys, if I also fix some gradient-like vector fields, I can define their Morse complex. So I make that choice. And then each of these Morse complexes are equipped with a non-Archimedean valuation defined simply by this formula. Here, the valuation of some linear combination of critical points is just the minimum of the value of the function for the critical points that have a non-zero coefficient, the usual thing. And then I also choose interpolating data. So, okay. So I interpolate between like Fi and Fi plus 1, and also the Morse smell this gradient-like vector fields, in such a way that the functions, okay, it just doesn't. So in such a way that the functions are always increasing in this S interpolation direction, and at any point. So I'm always thinking of this as like I have some kind of line, real line, and I have I'm going to map that real line into my manifold, and I have some data which depends on which point I'm on that line. So domain-dependent data. It's okay. It's constant near infinities and so on. But so then the outcome is that if you fix this interpolating data, you get these continuation maps. You can connect this Morse complex to this Morse complex by doing some other mode like that. Okay, and then these guys, these maps here, because I chose my functions to be increasing in the S direction, they are valuation non-decreasing maps, and they're quasi-isomorphism. Okay? They're inverse. You could also define an inverse which would not satisfy this condition, and those are not valuation non-decreasing. Okay, so now I have this diagram, this like Morse complex of first function, second function, and the map between them, the second function, third function, map between them, and so on. I can take homotopy colimit of this inductive system, and I can just use an explicit model like the telescope, but any model is fine. And then the key point is that after I do this, I get some infinite dimensional complex, and I degree-wise complete this with respect to this valuation that I define. Okay. So this is very important. I have to complete. Okay, so let's just
Maybe
yes.
If you take these functions and just thing itself. You can make it Lagrangian, say, in one-jet space.
Lagrangian.
You take the one-jet graphs of these functions.
Okay.
You get Lagrangian inside one-jet space of these functions.
Okay.
And there, all these Morse trajectories kind of correspond to homomorphic streets. So, what is this in terms of?
I feel like this is much simpler. It's just Morse theory.
Yes, yes. But the thing, the final limit.
Okay,
What
maybe.
is it in terms of this Lagrangian?
But it's just topological.
Yeah, at the moment, it's not subject to topology.
I feel like that's a much like let's
Okay.
maybe I should ask you again after the talk and try to understand what you're saying. But this is a much simpler situation. Okay, so for if you take a two sphere and take a disk inside this two sphere, let's just take a closed hemisphere, then the invariant that comes out of this construction is supported in degree 0 and is just one dimension. So the degree 0 generator, so you can think of constructing a sequence of functions which are kind of, so I have this disk, below it's like 0, and as it comes to the top, it increases and becomes flat and has some degree 0 generator in the compact subset and a degree 2 generator outside of the compact subset. All the functions that appear in the sequence are like that. And then I have these continuation maps which just send the degree 0 generator to the degree 0 generator, degree 2 generator to the degree 2 generator. But the valuations of these two generators behave completely differently. The degree 0 generator is basically constant. Degree 2 generator's valuation is going to infinity, plus infinity. So it will die in the completion. Okay, so that's kind of the basic idea of this construction. So I get something that even though each of the complexes, each more complex is quasi-isomorphic to the cohomology of the ambient manifold, this completed limit is not. And it depends on the compact subset. And you can prove that the result is actually the homology of the result being there. It doesn't depend on the choices by some kind of sandwiching argument. And a better thing to do is you can also just construct a much bigger diagram where you take all functions which are negative on the compact subset, and that's the only condition. And you only consider maps which are kind of that satisfy this increase in the S direction, and you form this kind of huge diagram. And you take homotopy colimit of the huge diagram that's completely canonical, and that you could and then you complete it, and that's your invariant, and all of these telescopes map into it in a canonical way. And those are quasi-isomorphic.
So does the fluid cohomology of the complex?
Yes. Okay. So I'm coming. It's the last one that appears. Yes. Yes. So I have restriction maps. If you use this kind of big model, you obviously get maps. If you use the smaller models, then you have to kind of cook up homotopy coherent diagrams to get maps. And if you use this big model, it's just a strict pre-sheaf. If you use the small model, then it's some kind of DG sheaf where you have to have homotopies. And it satisfies this kind of Mayer torus property. Okay, so here's the answer to what does it compute for an arbitrary compact subset? It's canonically isomorphic to check cohomology of this compact subset. Why check cohomology? Because it has this continuity property. So for a compact domain, it would just be any model of cohomology. But because it has continuity property.
Is it the same you can approximate by domain with smooth boundary?
Yes. So that's the so my student, my PhD student has like proved it. Right. Okay, so some remarks. So I want to refer to this kind of data of the sequence which converges to 0 inside and infinity outside as acceleration data. And if I don't complete, if I just take the homotopy colimits, then the resulting homology is just the homology of the ambient space. But actually, you could work with that too, because now you have kind of infinite valuation elements. And what completion does is it kills those infinite valuation elements at the chain level in some way that you can do homological algebra. how do you prove Meyer-Wiehe torus? So this Meyer-Wiehe torus, kind of you have to cook up data for like two compact subsets, like K1, K2, their union and their intersection in some kind of consistent way. And the way you do it, like the easiest proof that I know, goes by you kind of construct data for K1 and K2 in such a way that if you take the minimum of those two data, you get kind of data for the union, and the maximum for the two functions, you get data for the intersection. So there is some tension because the maximum and minimum of smooth functions is usually not smooth. So here you have this trick that if you're given two compact subsets, well, one compact subset you can always approximate by domains with smooth boundary, but you can also approximate two compact subsets simultaneously by compact subsets with smooth boundary in such a way that the intersections of these compact subsets and the union of compact domains and the union of compact domains are also compact domains with smooth boundary. You make them kind of, it's like cutoff functions, like bump functions.
Actually, suppose there's some stuff in sheaf theory, like manifold support and retarded sheaves by Lamarck. Did you ever look on it? It's kind of feeling what you're doing. It's
no, but I should.
Yeah. There was some notion that you multiply space by a line. It's the sheaves
Oh.
that you can propagate along the positive.
Yeah, this I looked. I didn't know that it's called the retarded sheaves. No, it's definitely very related. Yes, in fact, we wrote a grant with Tatsuki Kubagaki about relating it. But this is again simpler than that. So then, like, if you want to prove this general Meyer-Wiehe torus with K, like more than two subsets, you just do some formal induction because everything is well defined at the chain level. Okay, and just algebraic structures. So you can also equip a bigger model, like something that's quasi-isomorphic to it, with an E-infinity structure. So this is kind of, my student is also supposed to do this, but he didn't tell me he did it yet, so I didn't put his name. I really forced him to tell me that he did it, but he didn't do it. Okay, so you can do E-infinity structure, you can equip it, but and you can upgrade all the previous statements like restriction maps with respect this structure and so on. I will not talk about E-infinity, but I'll talk about A-infinity. Okay, so A-infinity is not the natural, and that's not the complete structure, but easier to talk about. I'll do that because I can only work with like, yeah. And my goal is, of course, to do this in Floer theory. So not Morse theory is just an exercise. Okay, so some basic stuff about operads that fix a base symmetric monoidal category. You can think of chain complexes if you want, or maybe simplicial sets. But you can work over it. An operad has this kind of multi-composition structure. So you can kind of, I think if you don't know what is an operad, then I'm not gonna be able to teach it to you in this 5 seconds. So hopefully, you know, I'm just reminding you kind of what kind of data it needs. It has this kind of spaces for every natural number, and then you have this multi-composition. And there are some examples. So like you can have associative operad, you can have A-infinity operad, Tashev polytopes form an operad, and you can also consider stable metrized rooted ribbon trees operad. And you can also consider nodal disks, stable nodal disks with mark points. You have these examples of operads. You can also talk about symmetric operads. Those also come with the symmetric group actions. And for those, you have the commutative operad. You have E-infinity little cubes, thin little disks. And you know, this I will focus on the non-symmetric structures today. And if you have any operad over any symmetric monoidal category and you have a monoidal functor from it, you can change the base category by that monoidal functor. Okay, so if you have an operad in topological spaces, you can take chains and get an operad in chain complexes.
Monoidal functor tensor form with morphism in one direction.
Morphism in one direction is enough. Okay, so I will also need to use a multi-object version, so a colored version of this operands. So, an operand, you should think of it as a multi-category with one object. So if you have like many objects, then you have kind of multi-morphisms, which can have one input, two inputs, three inputs, and so on, but always one output. Okay. And for this, I need a set of objects. Okay, so I already said that. And if I have this symmetric monoidal category that I started with, if it admits an internal home, then there is a kind of a good multi-category that I can immediately define, which has the same objects as the symmetric monoidal category, but I can define this multi-morphism spaces by this formula. Okay. So then a multi-functor between multi-categories is a map on objects, and then a map on multi-morphism spaces, and this should be compatible with multi-compositions. There's also compositions in, of course, multi-categories. And maybe the main thing I want to say in this slide is that if you want to, an algebra over a multi-category is simply a multi-functor from that multi-category to this kind of V bar thing that I defined. Okay. Okay. So now I'll also assume that some limits and colimits exist in my symmetric monoidal category. But okay, here's kind of the diagram that we use with Mohammed and Yuval to kind of define our structures. So we're going to construct some multi-category that's going to have a functor. So we can imagine here that V is chain complexes. Okay, let's talk about chain complexes, make it simpler. So we have from this kind of a big multi-category, what we call a Floer functor. Okay, this is on objects, it will take Floer cohomology. And on multi-morphism spaces, there's going to be some data that's picked on here, and that data will give you operations on the right-hand side. So this is going to be a huge thing, a lot of data, like all Hamiltonians, all Floer data, all everything. But for all of those, I will be able to construct such a functor. So this will be some kind of universal Floer diagram. Okay. And then from this kind of multi-category, I'll have a forgetful functor to an operand that only remembers the underlying Riemann surface. And the structure that I'll get is going to be induced by whatever operatic structure I have on that Riemann surface data. Family of Riemann surface. Okay. And that's why I'm given this map. And the construction is just going to do like follow blindly the formula for what people call operatic homotopy left-hand extension. Okay, it looks very fancy, but it's really just a formula, huge bar complex. It's like a generalization of just a homotopy colimit. If O was just a category with like a point category, so a category with one object and just unit morphisms, this would really just be homotopy colimit.
Can you say again what M is going to be in this example?
Maybe I get to it because that's kind of the main construction is the construction of N. Okay. That's the thing that's specific to the situation. The rest is just general algebra. Okay, and this left-hand extension is not just this map. So this map, let me just kind of maybe spell out the map. So this has just one object. So this gives me a chain complex. Okay, and for every element of the multimorphism space, I get an operation on that chain complex. Okay, so that's the data that's encoded in this arrow. That's arrow. So that's like the homotopy colimit as just the object. But the homotopy colimit also comes with the data of maps to the homotopy colimit. So that's encoded in a natural transformation here, which I will ignore. Okay, there's a lot of data there. Okay. So in the Morse theory case, I can tell you what these are going to be, except M is going to take a little bit more time. So here V is going to be chain complexes. And O is going to be some certain cubical chains on the moduli spaces of possibly broken, stable, metrized, rooted ribbon trees. Okay, so that's the kind of, if you want to get that's what you need. You need trees, you need to equip them with Morse data, and you need to map them into your manifold, satisfying some gradient flow-like equation. And you need to do it in families. Okay, so now let's just assume that we also have weak equivalences. So like we can just talk about chain complexes and quasi-isomorphisms. So I'm in this slide, I'm trying to tell you how we're going to formalize acceleration data in this framework. Okay, so acceleration data, I first define this category N, which is just a very simple category with one object for each natural number. And I have morphisms from I to J if I is less than or equal to J, and it's just one morphism. And otherwise, I don't have any morphism. I don't have morphisms going back. So acceleration data, what it's going to be is just, it's going to be a functor from this N to my big multi-category. So each object will pick for me a Hamiltonian, something like a Hamiltonian. Okay, and then if you compose the Floer functor from M to chain complexes with this inclusion, that's kind of this diagram that I started my talk with. Okay, that's this diagram with like Morse complex of first function, second function with the continuation maps between them. That's obtained in this way. Okay, so now I want to make a claim that this huge complex that I'm going to construct is computed by that like just small telescope. Like how do you prove something like that? This is related to homotopy cofinality arguments, like, but the assumption that I make is this. So for every sequence of objects here, there should exist a sufficiently large number such that after that number, if I look at multimorphisms out of this fixed collection to my kind of deep, sufficiently deep point in my acceleration datum, okay, every time acceleration datum, this guy should be homotopy equivalent to just whatever the Riemann surfaces give me in topology. The extra choice should be just auxiliary choice that is kind of up to homotopy unimportant. Okay, and it should continue like that. Okay, so for sufficiently large, so I have fixed objects. If I choose my output object sufficiently large, then just the homotopy type of the data that goes from these fixed objects to the fixed object outside is at output, it should just be the homotopy type of whatever the Riemann surface, choice of Riemann surface gives you. Okay. So then the canonical map from the telescope to the huge left Kahn extension will be a weak equivalent. And this is just a version of Killen theorem A. Okay. So this is how you go from huge models to just telescope small models that you could potentially compute. Yes.
Very dumb. So far, we're still just fixed. We have a fixed set K, right?
So we didn't, here I'm just talking about some general setup. I didn't even introduce how K is going to come in. So now we'll go back. So now let's construct this M in the Morse category, Morse homology case. So in the Morse theory with support, I want to construct a multi-category Morse X whose objects are Morse small pairs. Okay, so a function and a gradient-like vector field for that function. Multimorphisms. Okay, again. Okay, multimorphisms are just cubical sets of, again, possibly broken. This time it doesn't have to be stable. It's pre-stable, metrized, rooted ribbon trees equipped with a pair Fs, Xs at every point of the tree. Okay? And again, there are conditions, but the one that I want to highlight is this kind of monotonicity condition. Okay, so this is needed to make these maps, the maps that you get, valuation non-decreasing. Okay, so continuous. Yes. Okay. Some generalization of symmetrics, simplicial sets. Not generalization either. Just instead of using simplices, you use cubes. Okay.
So suppose your set has two connected components.
and you want to talk about the products, and you have product.
Okay, so but let me just continue. I didn't even tell you where the K didn't come in yet, so you have to wait for the K. Okay, so now I have I also have a forgetful map. So this map to O is just you have the data, you forget about all the data, you just remember the type of tree, and you stabilize. There are some pre-stable components, you have to stabilize them. And here I want to use a version of this this kind of tree operator, but actually it's better to use like not just compactify in the usual way and take cubes in it, but just like define a smaller cubical compactification where you only allow the generation of trees in particular ways. The technical point, but I think it's a kind of an important point, because this becomes really useful in third theory. Yes.
And at one point in your tree, you're given a global more smell there.
Yes. There are some conditions that I'm not writing, but like it should be constant at infinities. It should stabilize as only in a compact region the data changes. Yeah. Okay, and this kind of multi-morphism spaces. So I'm just trying to say that this kind of this kind of the extra choices that you, so if the objects, the functions that you fix in the inputs they're fixed, by choosing the output sufficiently large, you can make the choice of Morse data homotopically unimportant, is what I'm saying. There is a contractible choice. You can do convex interpolation basically between any two choices. Okay, and this contractibility, it says, again, I'm just like step by step saying that the homotopy type of the multimorphism spaces for sufficiently large output is determined by just the homotopy type of the trees that you fixed. Let me try to move on from there. So now I want to construct from this Morse multi-category a Morse functor to chain complexes, which is going to take, for every object, take its Morse complex. For every multi-morphism, it's going to give you an operation on the corresponding Morse complexes. But of course, for this, I need to restrict the regular data. I need to make moduli problems transverse. So then I have to kind of restrict my class of data and just consider regular data on these trees. But luckily, this does not change the homotopy type. Okay, this is kind of something that's nice. So if you have any kind of two Morse functions, then you can't connect them with one parameter family of Morse functions, but you can connect them with a family such that the moduli problem that it defines is regular. Okay, so this cubical sets, simplicial sets really kind of allow you to just kind of say this in a good way. Okay, so there's not really topological spaces anymore. This regular data, they really form just like simplicial sets. Okay, and then I can, when I restrict from to this regular data, then I can construct this Morse-Witten-Fukaya multifunctor. Okay, I have to take chains, and I can construct a multifunctor. Okay. So now comes K, finally. So K is, so I now consider as my M the full subcategory here with objects that are functions just that are negative on K. That's all. Okay. I restrict this Morse functor, and then I take left Kahn extension, and then I take completion of the entire thing with respect to the mean value. That's the resulting eigenvalue. If you want, so this has a structure over like whatever the chains over this trees is, but it's equivalent to A infinity operator, because you can kind of construct some chains, which you can call Boardman cubical chains on these kind of spaces. Maybe it's not so important. You can realize explicitly the A infinity operator by taking some specific chains that give you a smaller model of the chains over this operator. Okay, and then this huge thing is quasi-isomorphic to the completed telescope that I started with because of the formalism that I tried to go over. So now we can also have a descent statement that takes into account this A infinity structures. Okay, so I have the same map, but now kind of the left-hand side is an A infinity algebra, and the right-hand side, this check complex, you can equip it just combinatorially with an A infinity structure that only takes into account the A infinity structures of the pieces. It's like when you read like Bot 2, and kind of when they talk about kind of Maillard torus with kind of with wedge product for differential forms, they write down some formula for a product structure on the full kind of generalized Maillard torus complex. That's basically what I'm talking about. And you can more abstractly think about this check complex as the homotopy limit of the infinity algebra. So, okay, so I mean, this is a remark, maybe I should skip it. I'm just saying that it would be good to have a good mechanism to try to transfer these A infinity structures onto the smaller model. You can do it, but there is real data involved in this transfer. And I don't know if like a good way to formalize the data. But you usually know that they exist if you make some assumption. Okay, so now I can go to Floer theory. Okay. So if there are questions, maybe now I can answer. Okay. So now I start with a Liouville manifold, and I take a subset that's not necessarily compact, though I will mostly talk about compact case. It's allowed to be closed and conical at infinity. So I want to just tell you something about closed string theory first. So first of all, like here, instead of this kind of valuations by just evaluating the Morse function, I'm going to do Hamiltonian Floer theory, and the valuations are going to be given by this action function. So now I consider the multi-category. So instead of Morse functions, now I have to choose like Hamiltonian functions and almost complex structures and so on, and those are going to be my objects. Multimorphisms will be families of Riemann surfaces equipped with data that extends those at cylindrical ends and so on. But the formalism is the same. So I will consider this kind of multi-category with objects that are non-degenerate Hamiltonians that are like linear at infinity with respect to some choice of Liouville coordinate. I'm not fixing the Liouville coordinate. And I'm also fixing some kind of nice, almost complex structures that allow me to have like maximal principles. So those are the objects. And multimorphisms are defined using monotone Floer data. And this monotone, again, means some kind of increase in the S direction, but it's harder to say now because we have Riemann surfaces and there's not a canonical coordinate there. So you fix a canonical coordinate. That's part of the choice. So this is written in our paper. Okay, so for this, I can't give more details. Take it with Mohammed and you up. But you choose some kind of closed one form that gives you a kind of a coordinate on the Riemann surface, and along that coordinate, your functions are supposed to be increasing. And that achieves this non-decreasing valuation property. So that's neat. That in this context, it's needed for two purposes: this action non-decreasing property, but you also need it for like maximum principle, C0 bounds. Okay, so now if you restrict the genus 0, the outcome of the construction is a sheaf of framed E2 algebras. For every compact subset, you construct a framed E2 algebra, and you have a kind of a strict pre-sheaf of framed E2 algebras associated to each, well, not even compact, but this kind of closed subset that's conical at infinity. Yes.
So your K has two disjoint pieces. The product of one piece will not know about the other.
Why not?
You will know about.
Yeah, all of this is ambient. Okay, all the structures are constructed using ambient data. They're not like intrinsically local. That's why it's with support, not local.
But a posteriori, with its disjoints,
I don't. I'm not sure.
It's disjoint, but you can't build a good barrier between them. So you still can do it.
Okay, so some properties like if you take a displaceable, like a Hamiltonian displaceable compact subset, then its symplectic cohomology will vanish. Okay, so this is kind of like this. This tells you, yeah, like this is an important property. Like you don't have, like in the topological case, in the Morse theory case, there's not that many subsets that have like just vanishing invariant. But in symplectic case, there is. If you assume that this subset is a compact Liouville subdomain, like those I considered in the first lecture, then this just recovers the Viterbo symplectic cohomology of the completion. Not a trivial statement, right? Because the structures in here that's in the symplectic cohomology with support, they're defined, like I said, using ambient data. You have to prove that it indeed is only dependent on local data. It takes some proof. If you take the boundary of this domain, then that's just Rabinovitz Floer. Okay, so descent now holds not in general. You don't have Meyer-Werthers property in general. You need a condition. Okay, so the condition is called Poisson commutative. I'm only going to say it for compact subsets, and it's not written for the non-compact case. And I think there is, like I thought about it a little bit, you do need some new technical ingredients as far as I can see. But in the compact case, so I have a kind of finite in compact sets. When can I recover the invariant of the union by the invariant of the pieces, the intersections, the maps between them, and so on? So you can do it when these subsets in question are Poisson commuting, which you could say in this way. You should have a smooth map from M to Rk. You should think of this as like a Lagrangian torus fibration, some more general version of Lagrangian torus fibration, an involutive map, such that the components of this map are Poisson commuting. Okay. And if you take compact subsets, so this should be if you take compact subsets from the base and you pull them back, if your original compact subsets are obtained that way, they come from the base, then you have this set. You have this Meyer-Werthers property. Okay, so the point here is that you can try to do this approximation by kind of compact domains simultaneously idea, but now there's going to be a problem if you don't assume anything. The kind of boundary dynamics of these subsets in question, they're not local. You can start some closed characteristic can start on K1, go to K2, come back and contribute to an orbit in K1 union K2, and you don't see it at all in K1 or K2 or K1 intersect K2. So you don't want that to happen. So you want to kind of have an assumption that blocks the separates the boundary dynamics of K1 and K2 from each other. So you need to have that, but it happens to be the thing, like it happens to be useful in mirror symmetry. Like we have that always because we work under the assumption of some kind of S5Z fibration.
But if there is some other form. If there would be interaction, there is some other form.
I don't know. I don't know for that. There might be, but I don't cover it. So now let's also include a Lagrangian. And now let's take an exact conical at infinity Lagrangian braid. Then instead of looking at like there, I was looking at Hamiltonians that depend on S1, periodic Hamiltonians. Now I'm looking at Hamiltonians that depend on 0, 1. And this Hamiltonian should make the Lagrangian kind of transverse to itself if you move it with the Hamiltonian field. Okay. Now this is going to be the objects of your multi-category. And again, if you restrict to genus 0, the outcome is like a DG. It's like a sheaf of A infinity algebras that can be computed at the linear level using acceleration. Okay, so for each Lagrangian that's exact and conical at infinity, now I have this kind of, for every compact subset, in fact, conical at infinity, closed subset, I can associate an A infinity algebra, and they form a pre-sheaf. And if you wanted to compute the underlying chain complex, you could take an acceleration beta and compute the telescope and so on. And you can also extend the construction to Fukaya categories. But now what changes is that the operand that's in the base, this O, that's also going to have colors. Okay, the colors. So the O previously was just kind of keeping track of the Riemann surface data. Now it's going to be like a cover of that where, so let me say, so like, so I have to, each object of this O in the base now is like a pair. It's not just one object. It has, for every pair of Lagrangians that I want to consider, that's an object of my multi-category. Okay, and I'll have like so now I have like L1, L2 object, L2, L3, L4 object, L5, L6 object, and output like K1, K2 object, let's say. Okay, the multimorphism space downstairs is going to be equal to the relevant kind of disk moduli space only if the Lagrangians match. Okay. So this will give a presheaf of A infinity categories. It's going to satisfy check descent if you have the same Poisson commuting assumption. Okay. So now, if you want to do this with closed symplectic manifolds, now you can't complete with respect to action. There's not a well-defined action. So you do something more stupid. You just kind of have Hamiltonian Floer complexes are generated by these like one chords or one periodic orbits. They are given valuation 0, but you work over the Novikov ring or the Novikov field where the ring and field itself has a valuation, and you do completion with respect to that. So the closed string construction is basically the same. For open string, now there's a new difficulty. There's curvature. And okay, I mean, we spent years trying to write something about this. And I don't know. Maybe, yeah, I'm not sure if this group is the right group, right? I don't. Hopefully someone else. So what we're doing now is that we settled on just writing something for tautologically unobstructed Lagrangian branes, and we're going to hopefully write that soon. So again, even though the morphism spaces are this time even more huge than before, like we can compute them, and kind of the intuition is that if you have a Liouville domain embedded into a symplectic manifold, if you shrink that Liouville domain a sufficient amount, the invariance that you get with support should be like deformations of the local invariance. And if you're in the case of an SYZ fibration, if you look at kind of neighborhoods of fibers, what you expect is that you are isomorphic to local invariance, but not canonical. The isomorphisms differ by what people call wall crossing isomorphism. But yeah, like there was some interest, but that's why kind of in the topological case, in the Morse theory case, the isomorphism is canonical. Here, the isomorphism exists, but not canonical. Like you could think that it depends on the choice of an almost special, almost complex structure. But if you choose another special almost complex structure, then the maps, there's the local invariance, which doesn't change. There's the kind of support invariance, which might change. And you get, in order to make the diagram commute, you need to kind of add a wall crossing isomorphism. Okay, but this is really kind of philosophical. Okay, so let me kind of try to tell you the outcome of the construction in this case in some kind of like kind of ignoring the formalism, just telling you here the chain complex, which I get as the morphism space between so I have Lagrangian L left and L right, and I have the Fukaya category with support. I want to tell you what is the morphism space between L left and L right. Okay, it's going to be a huge chain complex. So it's going to have some ends indexed by Lagrangian and Hamiltonian labeled planar trees. Okay, so here is my Lagrangian left, Lagrangian right. Here's a tree that's embedded in the plane. And for every kind of, for each of those components, if you take the complement of the tree, for each connected component, you're free to choose any Lagrangian that you want. Okay, so that's the Lagrangian labeling. And for every edge, you're free to choose any Hamiltonian that you want, which is going to be used to do Hamiltonian Floer theory with one course from the Lagrangian on the left to the Lagrangian on the right. Okay, and these H's are the multimorphism spaces. Okay, so if I have a K in place, these Hamiltonians are all going to be negative on that K. And finally, I have this O. This is just the Riemann surface opera space. Okay. So now for each T like that, I will construct a module over the Novikov ring, and I'll take the completed direct sum of all of those summits. Okay. So for incoming semi-infinite edges here, I just so like that one, that one, that one, that one, that one. I have a Lagrangian Floer complex for each of those edges. Yes. Yeah, so H means that I'm going to consider, like, H is the multi-category of Hamiltonians, and O is the opera. So I have fixed. I didn't tell you yet, so maybe when it comes. So I told you what. So now I'm trying to tell you to this tree how you're going to associate a module. I didn't tell you. So the first bit is you do Lagrangian Floer homology between like LL and L1 with the Hamiltonian HL1. Okay.
That's the data vertex too.
Yes. So coming. So for each vertex that's not adjacent to the semi-infinite outgoing edge, we have the corresponding H multimorphism chain complex. Okay. So here I have those fixed Hamiltonians, and then I have the kind of data of Floer data that extends those Hamiltonians in my multi-category. That's a chain complex, the multimorphism space, with those incoming Hamiltonians and the outgoing Hamiltonians. I take all of them. Okay, that's another chain complex. For O, I only take the I just take the corresponding chain complex and the opera. The Riemann surfaces, and then you take the tensor product of all of them. So incoming edges keep track of it's just if you think about it, it's just bar complex. I'm just trying to spell out the what's happening to the bar complex. So I have these kind of Hamiltonian Floer complexes at the top, multimorphism spaces for each vertex, and for the last vertex, I just have the operant complex. I take the tensor product, all of them, and then I can equip this with a bar differential. The differential takes into account how these operations defined by these vertices act on Floer complexes and compositions in my category. And finally, at the final step, you have to first project them and compose it all. I take the forgetful functor and compose it. Or is an opera. So it has a multi-composition.
But completely, what will it be? I mean, now I have that split, first of all, you input the rule of split and infinite of two Hamiltonians.
So inside O, you forget the Hamiltonians. You just have the Lagrangians. And then you have kind of so now the Lagrangian data does not impact the output. It's just the cubical chains on the moduli space of disk with 3 inputs and 1 output. No, 2 inputs and 1 output.
I think completely forgotten the Lagrangian data and material.
Well, the Lagrangian data just acts as like the brain. That doesn't change the choice of the disks. Yeah, they're just domain disks. So the only place where I do something tricky is the top level. The top level, I do Floer theory, and then I have like those are Floer complexes, and there's this action of H, which is like exactly, that's like the operation that you define by counting kind of Floer moduli spaces with inputs, outputs.
The vertices in the middle, they don't have solutions to suitable Homological equations. They actually have families of suitable Homological equations, but not solutions.
Yeah, solutions only appear at the top level. And the bar differential really made.
Where are the action solutions?
The very top.
At the very top, when I say action, the H acts, these multimorphisms act on the modules, I say, act on Hamiltonian Floer complexes, then action is by counting kind of solutions to moduli problem.
Right, so here there's three levels, and you're saying the first row of H's we actually have maps, the second row of H's we no longer do, just the data, and the last one we no longer have the data.
Yeah, so like here, so the top incoming semi-infinite edges, you put the Lagrangian Floer cochains given by those Lagrangians with that Hamiltonian. Okay, and then for every, so now, sorry. So now if you look at this, for example, there is a map that takes kind of, so you have there is a map from like the Lagrangian cochains from LL to L1 with HL1 tensor, L1, L2 with H12 to LL, L2 with HL2. There are those maps. So each element of that H in that vertex gives you a map like that.
Sure.
Okay.
So that is actual honest Floer.
Yeah, that's honest Floer theory, yes.
But we include all the choices.
You include all choices, all families, everything. Yeah. Yeah. So that's the bar complex. And the point here is that we needed all the action of the operand, and now we have that. That's all we gained from this huge thing. What we do is we take two trees like this. You have an element of O, you graph them, you compose in O, and then you get a tree of this form, and that actually lifts to these underlying chain complexes and gives you an action. Yes? But I mean, I think you say it's painful, but I don't think it's more painful than like Mohammed and Paul's paper. Like, because there you have to like actually do some like smart work. Here you just have to blindly just like follow whatever the algebra gives you and just construct your functor as general as you can. Like, there is not something smart that you have to do.
I understand, but you don't see the geometry because it's all.
I disagree. I think you actually see the geometry more directly. The operand is there.
I think I need
Like
to
the
read
operand is, huh?
I think I need to read the paper rather than see the stuff.
I don't know. Okay, hopefully that will help. But yeah, okay. So now, so how much time am I over?
Not yet. No, like 6-7 minutes.
Okay, great. So now let me explain to you this strategy for homological mirror symmetry. So we start with a closed graded symplectic manifold and an object of Fukaya category. Okay, this object is supposed to be the object. If you do have homological mirror symmetry, it's the object that maps to the structure sheet. Okay. You take a Poisson commuting cover by compact subsets. And you consider this full subcategory of the ambient Fukaya category, which is the objects that are split generated by this Lagrangian in each of these small Fukaya categories. Okay, so this is something, it's not, this L is not going to, it's like the structure sheet. The structure sheet doesn't generate the derived category, but locally it does for an affine variety. It does, the perf, not derived category, but perf, it does. So that's kind of what we're mimicking here. Yeah, so it's going to be, I mean, typically you'll have something like an SYZ fibration and cover the base and take pre-images of that. And L is going to be a section of the SYZ fibration. Okay, so now for each local, so this capital I notation means I'm taking intersections too. Okay, so a subset of the finite set that indexes the members of my cover. And you have an endomorphism, A infinity algebra of this L that I fixed in each local category, small category. Okay, so that I call AI. So now, under this kind of a lot of assumptions, which are basically all kind of weakenings of this SYZ geometry, you can prove that these AIs are actually topologically finitely generated commutative algebras in degree 0. Okay, so this is I mean, you have to say a lot to justify this. And moreover, the restriction maps that you get give you inclusions of like sub-affinoid domains, like domains that you can use to glue different spectra. Okay, so here's the diagram that I tried to introduce in my previous lecture. But because this lecture was going to be painful, I gave that entire lecture so that I could introduce this diagram without the pain. Okay, so the diagram goes like this. So I have this kind of subcategory of Lagrangians that are locally generated. Okay, so then those map into the check. Those map into the check complex of those Lagrangians, but inside this kind of smaller things, smaller open subsets. You can skip that if you want and just map directly to the homotopy limit of those categories. Okay, so I'm introducing check because the descent statement is actually about this check complex, not about the homotopy limit. Homotopy limit has a lot more objects. Okay. And then, so because we have this, because we just chose it to be split generated, I have this functor from that homotopy limit to the perfect modules over that algebra. AI. It's just the restricted Yoneda functor. I just test with that object. Okay. And then finally, this homotopy limit of these perfect modules is a DG enhancement of perfect complexes over this Berkowitz space Y. Okay. So now I have obtained an HMS functor that's cohomologically fully faithful from that subcategory to the perfect complexes over the what's supposed to be the mirror. But now there are some questions that you should ask, which is that how big is this category, this FLK? Okay, how big is the category, subcategory of Lagrangians that are locally generated? So hopefully they split generate. So the statement that you're hoping for is that if you choose your cover sufficiently small in the SYZ case, it will split generate. And then there's another question, which is that how big is the image here? Do they split generate? Okay, so this is some version of this core, like the format is like this core homological mirror symmetry, something like that. Okay, so let's do it for the torus. So for the torus, I can just use this fibration to a circle, and I have a Lagrangian section that's just this section that's blue Lagrangian. And first of all, if you just compute the local algebras of the blue Lagrangian on cylinders, you get this non-Archimedean annulus, functions on this non-Archimedean annulus. And then you can cover the base circle, so this guy, with like 3 intervals which don't have a triple intersection. Okay. And then you're going to have 3 of these algebras, and then you're going to be able to glue them along smaller sub non-Archimedean annuli. This is like your picture. This is like the picture in your paper, those papers. So then you're gonna, by this gluing procedure, you're gonna obtain a Tate elliptic curve, non-Archimedean elliptic curve. And here, okay, so now I already have my kind of FLK. I have my mirror. I have the HMS functor. All I need to prove is that they split generate. And this is true in this case. Okay, so I'm not saying it's obvious, but it's true.
So do you need 3 or could be 8?
No, it could be 8.
Oh, yeah, just if you do only 2, then you have the.
Yeah, that's only reason.
Okay.
Yeah, so the reference section, this blue section, maps to the structure sheaf by construction. You can check fibers map to skyscraper sheaves under this HMS functor. But what I want to highlight is that another, like any Lagrangian section, maps to a line bundle. Okay, and here I have this kind of blue Lagrangian, and I take some section that's this red Lagrangian. Okay, and this is one of my, let's say, one of my intervals, and this is another one of my intervals. So now the point is that if you, let's say this is some intersection point between them. The point is that if you look at the local category, so the category of this cylinder, this P1, this intersection point, is actually an isomorphism in that category. It's not globally an isomorphism. In each piece, you have to choose a different intersection point to get the isomorphism, so you don't extend to a global isomorphism. But because it's an isomorphism, these are like your local trivializations. And in order to compute which line bundle you get, what you need to do is to compute the transition functions, transition maps. Okay, so so I have this kind of spec AI. The module is given by this. I have this kind of action by the local algebra. This is the local module. It's just the pair of pens product. Like this, that's where this is.
Well, there's a question.
Yes.
Wait, is the local on the Berkovich side, is the local generation automatic?
I think so.
Okay.
Because it's smooth. So
Okay.
even if it's not smooth, it's not automatic. I mean, like a affine variety, it's perfect complexes is always generated by O.
Yeah, just trying to understand where the.
And you're just asking if this is still true.
Oh, like okay.
Yeah.
I think so, but
Okay.
but I might not be the right person to ask the question. But yes, I think it's true.
This is where I'm wondering where the subtle.
So for us, we just take that as the model.
Yeah.
So another silly question. When you the argument for like sections mapping to line bundles, that assumes the pieces are small enough that the sections are locally isotopic to the reference section. If you did
Do you have to take them to be very small in this case?
well, I think enough that the mirror pieces are affine.
Well, in general case, yes, you have to be careful. I'm just giving you in the torus.
Oh yeah, for the torus.
Yes. Yeah. In general, you have to be.
I mean, if you had a multi-puncture torus, you couldn't take more than.
Yeah, let me just add with the torus.
Yes, okay.
Yeah. So for trivializations, what do you have to do? Well, you have that intersection point pi. You have that restriction. So pi is like this, an element here. So it has a restriction map to the like I plus one version of it. So you have one element coming from pi here from ki, and another element here coming from ki plus one. So these you have two elements in the same module, and you have to find which element that you have to act by to get from one to the other. That's the transition map. And you can compute it. Like in this case, the transition map is just given by multiplication with a generator that wraps around once here. Okay, and now I'm gonna finish. I hope I didn't exceed. So there is a local generation package that Mohammed's gonna talk about, I think.
I'll take it.
And then kind of he's also gonna talk, I hope, about this kind of why local generation is gonna maybe satisfied if you choose your kind of your neighborhood sufficiently small. So I know in this version, I know of no strategy to prove B-side like split generation. Like I don't know why this functor should be essentially surjective. I don't know. And the mirror may not be algebraic at all, so you have to work in this kind of non-Archimedean setup. And maybe one should write a paper about what corresponds to this, like Verbitsky's result on like, if you have a non-algebraic analytic K3, then the derived category of coherent sheaves is basically like independent of the K3. So in the Fukaya side, there's also something like this.
Torus is a rational form that
Yeah, but I don't want to just get a zero category. I want to get something that's interesting that's actually happening, but not you can see it in the category.
No, but I think with Torah you can smell do examples with.
Okay, I give up. Yes. Yes. Torus is the way to go. Yes. So I think this is a lot of machinery. Probably the first interesting to do with this machinery is to do something about this. I'm not sure what's going to come out. Yeah. Yes, I'm done. Thank you.